In our first submission to the Kaggle competition on credit card fraud detection, we got a score of 0.9 AUC by just throwing cat boost at the raw data. But in this video, we're going to apply the technique of ensembling to improve that score to 0.94 AUC. So let's get started. The previous video had this sandbox document. Now I've created one called Ensembling, which is a copy of that with a few modifications. But some of those modifications lead to considerable performance improvements, so I want to work through this. So onto the feature engineering. I didn't do anything fancy here because I wanted to see explicitly what ensembling was giving me in terms of a performance benefit. So the only thing I did was count the number of nulls in the train and test set. The other thing I did was I removed numbers from the columns ID 30 and ID 31, and that's because if you look at these columns, you'll notice that they're operating system versions. So for instance, Android 6.0.1. And I noticed that in the test set, there were operating system versions that didn't exist in the training set, because the test set is further in the future than the training set. So to quickly get around this issue, I just removed all numbers. This is important because the model doesn't know what to do with categories at prediction time that it never saw in training. This is one way to get around that. And instead of overwriting the original columns, I went ahead and created two brand new ones, and then that way the algorithm can decide which is best for the problem at hand. So I mentioned in the beginning that I used LightGBM in this ensemble. And I did that because I noticed on the leaderboard in the discussions of Kaggle that a lot of people were having success here. And it wasn't a library I was previously familiar, so I wanted to try it out. Okay, so one of the nuances for the LightGBM library is that instead of passing in the raw character string for a category, you need to pass in an integer that represents that category. So I use the pandas categorical dtype object for doing that, and you just need to specify all of the unique categories, and I use the training set for that because I don't want to cheat by looking at the test set and giving myself additional information that I wouldn't be able to have in a production environment. So I use this new data type and I extract the category and the codes. And I go ahead and return the train and the test because this ensures that my mappings for a particular category are consistent across these two data sets. So I go ahead and fill in my categorical missings with this bracket unknown as I did in the previous video. My addition here is that for the numeric, I also fill in -999. And since I'm using a tree-based method, it should easily be able to pick this up as being something special. Whereas if we were using logistic regression or something like that, this would not be a good idea. You'd want to fill it in with the mean value or something like that so that you didn't get any outliers that were greatly skewing your loss function. And this is where I call the function just defined to map each of the categorical columns to an integer value, which will now represent that for the LightGBM library. Okay, so on to the modeling. Just like previous, I'm using cat boost to start. One of the differences, I'm defining a validation set here, which is the last 5% of the data after you sort it by time. And then I define this object called dfTrainSample as being everything that's not in the validation set. Okay, so a validation set is going to help me tune hyperparameters because it gives you an estimate of performance on the data that wasn't used for training. Your model is always going to perform much better on the data that was used to train it than data that it's never seen before. In the fraud domain in particular, you're dealing with an adversary who changed their behavior in response to the models designed to catch them. So you always want to train on the most recent data. On the other hand, you always want to validate on data in the future so that you don't memorize patterns that aren't important anymore. So you have a catch-22 situation. You want to reserve some data so that you can accurately estimate your performance, but you want to use as much of it as you can to train. So I've tried to have my cake and eat it too by ensembling models from both approaches. So we'll step through the details of that. Another change I make is using a weight on the fraud samples in the cost function, and that's to address the class imbalance problem. One strategy to address class imbalance is artificially duplicating some of your fraud samples to close the gap in class imbalance, and this is called upsampling. A similar approach is using a weighted cost function, where you multiply the mistakes for the minority class by some weight, which sort of simulates what it's like to have multiple instances of that example. The weight that you apply can be considered a tunable parameter, but in my experience I find simulating around a 20% fraud rate works pretty well. So another change is the parameters used to train the CatBoost model. So here is where it's leveraging the weight for the positive class, as just mentioned. I'm also using the GPU implementation, and I gave a lot more iterations and a smaller learning rate. So typically, if you want to improve your accuracy, giving more iterations at a smaller learning rate is a great way to go. But if you want to train fast and kind of get some quick results, using a higher learning rate and smaller iterations will help you speed up. When I use these parameter values, I end up getting an AUC of around 0.953 on the validation set, which again is the last 5% of the training data. Okay, so now I go on to the LightGBM library. So they have their own data structure that they call a data set, which is very similar to a pool. You pass in the raw data or the feature data, you pass in a label, which ones are categorical. The difference here is that instead of passing in cat calls, which are my categorical columns, I pass in the encoded versions, which are the integers instead of the raw strings. To get the parameter values, I just looked at someone else's kernel, which I've linked to here, and they had done some sort of hyperparameter optimization and gotten these values, which I copied and pasted. So the only change I made to this is I included the scale for the positive class, and that's exactly what I did in the CatBoost model. And again, this is just to give extra importance to the fraudulent samples since there's a significant class imbalance. So I go ahead and train this using 3,000 rounds and get an AUC on the validation set, again close to about 0.95. So if you plot these ROC curves, the CatBoost and the LightGBM are almost on top of each other. So at this point we have two models, one from CatBoost and one from LightGBM, and they're both trained on the first 95% of the training data and are validated on the last 5%. But, as previously mentioned, we typically want to use the most recent data to build our models because that will give us the strongest signal, and that's because fraudsters quickly adapt their behavior. To take advantage of the most recent data, I use a different strategy for cutting it into training and validation. Whereas before I sorted by time and took the most recent for validation, here I ignore time and I just randomly sample some portion and give it to train, and then the rest is used for validation. And that's implemented with K-fold from scikit-learn. So here I'm using 5 different splits and training a model on a random sample, which gives me 5 different CatBoost models. So you can see the performance for each of the 5, but they do roughly the same, and I use the exact same parameters as the full model from before. Each of these 5 models is trained with a different sample of the training set. And whereas the first model couldn't see the last 5% at all, these models can. So if you take all 6 models independently, they should have a slightly different view on what it means to be fraud. And when we average their predictions, we'll ideally get a prediction that's better than any of the individual models could have given us by themselves. If you plot the CatBoost model scores against the LightGBM model scores, you'll notice that they don't just fall in a straight line, which would mean that they're assigning the same scores to the same accounts, but there's actually quite a bit of variation. And that tells us that these models have a different perspective on what it means to be fraud. This in turn gives us hope that by ensembling these 2 models together, we might get something better than either of the individuals. To get my final model score, I averaged together the scores of the 7 models trained in this notebook. So that's the first CatBoost, the LightGBM, and then the 5 CatBoosts from the cross-validation. When I upload that, I get my performance of 0.9407, which I'm currently 884 in the leaderboard, which is in the top third for a population of around 2630.